Now that we have these ideas of basis and dimension, you realize that being able to come up with a basis for a vector space is actually pretty important. But sometimes you want a basis that either you want to build a basis out of some vectors you already have, or you want to somehow come up with a basis that is well adapted for the problem that you have at hand. So it pays to have some ways to build a basis or know when you've arrived at a basis. So along those lines, let's ask this question: if we're in a finite dimensional vector space and we have a linearly independent set, can we grow it to form a basis? Suppose we're in a vector space V. Let's say the dimension of V is n, and we have some collection. Maybe I should be putting them in order. V1 up through Vk, and we know that this is linearly independent, but also k is less than n. So we have a linearly independent set, but it doesn't yet have enough vectors in it, right? Well, since k is less than n, let me call this b sub k. So I'm calling this b, but it's not a basis yet. I have a reason for calling it b sub k, right? K, in what we're about to do, k is going to be the number of vectors in this list. So we know b sub k is linearly independent. It can't be a basis because it doesn't have enough vectors in it, too few elements. Well, look, if it's not a basis, but it is linearly independent, then that means that the span of this set can't be V. If this set b sub k did span V, we'd have a spanning set for V that was linearly independent. We'd have a basis, but we know b sub k isn't a basis. It's not big enough. So that means that the b sub k can't span all of V. So take any vector v sub k plus 1 that is in V, but not in the span of b sub k. All right. Now we've seen that if you have a linearly and then let's let b sub k plus 1 be, I guess I need angle brackets, v1 up through v sub k minus plus 1. Now we've seen if you take a linearly independent set and you add to it a vector not in the span of that set, the result is linearly independent. So now we know that b sub k plus 1 is linearly independent. Well, look, now we're back where we started. We have a linearly independent collection. K plus 1 might not yet be big enough, so we can just repeat the whole process. Right? Repeat until we get down, right? If we don't yet span all of V, then take some vector not in V, add it to our collection, and now we have one more. Do this enough times and you're going to get to a collection of size n, right? And it will be linearly independent because, right, at each stage in the process, we're choosing a new vector not in the span of the previous vectors, and we know that that results in a linearly independent set. So now we have a linearly independent set with n vectors. Now the question is, could this n vectors, does this n vectors span V? Okay, well, capital V. How can we tell if it spans V? Well, just take a vector and see if it's a linear combination. So let's take an arbitrary vector little v and capital V. We want to know, is it a linear combination of V1 through Vn? So we know that the collection of v1 through vn together with v is linearly dependent because it has too many elements in it. It has n plus 1 elements, right? We know that in a n-dimensional space, the maximum number of linearly independent elements is n. Well, we have more than that, n plus 1. I guess, again, I should be using angle brackets here. So that means that these are linearly dependent. So write a linear dependence relationship. Zero vector is a1 v1 plus so on up through an vn plus a times v. Now, we can't have, a has to be non-zero. Because if a were 0, we would have a linear dependence, non-trivial. I need non-trivial here. Non-trivial. Okay. Well, a has to be non-zero. If a is 0, we have a non-trivial linear dependence relationship among v1 through vn, but we know that that can't happen because v1 through vn is linearly independent. So that means a is non-zero, but then we can solve this equation for v, right? V is minus a1 over a times v1 plus and so on down to, I guess, minus, not plus, a n over a vn. All right, so now we've displayed v as a linear combination of v1 through vn, so we know that bn spans v, yes. Right, so we started with some linearly independent collection. We've successfully expanded that to a basis for the entire space. So if you start with a linearly independent collection, you can always enlarge it to a basis. All right, well, that's if you start with something smaller than a basis. What if you start with something bigger than a basis? So what if you're in a finite dimensional vector space and you have a spanning set? Is it possible to throw away some vectors and end up with a basis? So let's say our vector space is V and say it has dimension n. And let's say that this spanning set, let's call it B sub k. All right, so B sub k is going to be some collection of vectors, v1 through vk. We don't know how big k is, that's the problem, but we do know, we're assuming that the span of B sub k is all of v. Okay, now, the question in the back of our minds is B sub k a basis? We can't tell yet because we don't know if B sub k is linearly independent. So if B sub k is linearly independent, then what we actually have is a basis, right? We already know B sub k spans V. If it's also linearly independent, then B sub k is a basis. And then we know k has to be equal to n, and we're done because we have a basis. So what if it's not? If not, so if B sub k is not linearly independent, then that means it's linearly dependent. So some vector in B sub k is dependent on the others. Okay, and let's say, for the sake of argument, that it's actually V sub k. Right? If it's not the last one, then rename all of them so that it is the last one. Okay, so that means V sub k is a linear combination of V sub 1 through V sub k minus 1. All right, well, something that we've shown in the past is that if a vector is a linear combination of others, then throwing away that vector doesn't change the span. So now we know that, I guess, let me throw away the last vector, and let's call the result b sub k minus 1. So b sub k minus 1 is v sub 1 down to v sub k minus 1. Then we know that the span of b sub k minus 1 is equal to the span of b sub k, right? Because we threw away a redundant vector. But we know that the span of b sub k is all of v because that's what we assumed, right? All right, so now we're back where we started. We have a spanning set b sub k minus 1, and we don't yet know if it's linearly independent. So we can repeat the whole process, right? If it is linearly independent, then we have a basis, and we're done. We've reduced our spanning set to a basis. If it's not linearly independent, then we can throw away another vector and without changing the span, and that would give us b sub k minus 2. Now, eventually, at some point, this process has to terminate. So, all right, eventually. Right. If we keep throwing away redundant vectors, at some point, since we started with finitely many vectors, at some point, if we keep throwing away redundant vectors, we have to end up with a linearly independent set. Now, we don't know when that is, but let's say it's at step L. Okay, so this is eventually linearly independent. And the reason that we have to eventually end up with a linearly independent collection is because eventually we're going to be down to one vector or zero vectors, right? If you're down to one non-zero vector or no vectors at all, that is linearly independent. So eventually we end up with a linearly independent collection. But remember, at every stage in this process, including the last stage, the collection of vectors spans V. So now we have a linearly independent collection that spans V. In other words, we have a basis. So this thing, B sub L, is a basis, right? And furthermore, since it's a basis, right, we know the dimension of V was n, so the number of vectors has to be n, right? So now, in retrospect, we see that the number of vectors we started with had to be bigger than the dimension of the space. So, right, side note, k was bigger than n to begin with. This wasn't obvious, or this wasn't something we assumed at the beginning, but now in retrospect, that had to be the case, or else we wouldn't have been able to span V. So the upshot of all of this is, right, if you have a spanning set that's too big, you can cut it down to a basis just by throwing away redundant vectors until they're linearly independent. And if you have a linearly independent set that's too small, you can make it bigger to get a basis. Right, so always, if you're dealing with a finite dimensional vector space, you can always get a basis somehow. That's the idea.